Hello and welcome back to Learn Mechanical Engineering with SOLIDWORKS. In this lesson, we will talk about free undamped vibrations. We have a system that has a mass and spring, and we are required to find the natural frequency for this system, as well as the displacement equation. To solve this problem, we will go through 3 steps. First, we will draw the free body diagram. Then, we're going to derive the equation of motion, and finally, we're going to put it in the standard form. Let us start with the free body diagram. We can see that there are 4 forces acting on the mass: the weight of the mass, the normal reaction force, the friction force and spring force. The weight of the mass and the normal force cancel each other out. The friction is neglected on the analysis, so we're left with the spring force acting on the left side. To drive the equation of motion, we say that the sum of the forces in the x direction is equals to the mass times the acceleration. Acceleration is the second derivative of the displacement. So we get minus kx equals mx double dot. We arrange the equation as mx double dot plus kx is equal to 0. To put it in the standard form, we divide by m. We get x double dot plus k over mx is equal to 0. The natural frequency is given by the equation omega n is equal to the square root of k over m. Let us assume we have a system that has a mass of 25 kilograms and stiffness of 4,900 Newton per meter. Then, we substitute the values, and we get omega n is equal to 14 radians per second. The general solution of the second-order differential equation is given as a sine omega nt plus b cosine omega nt. We use boundary conditions to solve for a and b. Let the initial displacement be 20 mm, and the initial velocity be 0. In the displacement equation, we sub in the value of x equals 20 mm, at time equals 0. We get b equals 20 mm. Now, we differentiate the displacement equation. We sub in the value of the initial velocity, and we get a is equal to 0. So, the displacement equation after substituting the values of a and b, x equals 20 cosine omega nt. Now, to validate our calculations, we head to SOLIDWORKS to create a realistic simulation. First, we open new part, and we draw square on the top view. Dimensions are not important cause we will override the mass using the mass property tab. So let us give it a dimension of 200 mm for the argument's sake. We extrude the sketch to 200 mm, and we select mid-plane. Then we save the part as mass. We open a new part again. We create rectangular on the right view with the dimensions 200 mm width and 400 mm length. After that, we extrude the sketch to 20 mm, and we choose mid-plane. Then we save this part as fixed wall. Again, we open a new part. We create rectangular on the top view with the dimensions 400 mm width and 1000 mm length. After that, we extrude the sketch to 20 mm, and we choose mid-plane. Then we save this part as ground. Now, we open New Assembly. We insert the 3 parts we just created. We make sure all the 3 parts are free to move. Then, we choose Mate, and we add constraints as follow. Coincident constraint between ground and assembly origin, top to top, front to front, and right to right view. We make coincident constraint between the mass front view and the ground front view. Then, we choose the mass bottom face, and we make it coincides with the ground top face. We make coincident constraint between ground front view and the wall front view. We choose the back face of the wall and we select the end face of the ground and we make coincidence constraint. After, we select bottom face of the wall and top face of the ground and select coincidence constraint. We can see that the mass is free to move in the X direction, while restricted on the other directions. Lastly, we save the assembly. Now, to do the simulation, we go to Motion Study. Select SOLIDWORKS add-in, and select the SOLIDWORKS Motion tab. After it's activated, select it in the simulation window. We add a distance constraint between the mass and the wall. The value is 400 millimeters. Before we forget, let us override the mass property. Select Evaluate tab and select Mass Property tab. Clear the selection window, then select the mass. Click Override Mass Properties and select Override Mass. Enter 25 kilograms and click OK. Go back to Simulation window and select the spring icon. Select this face and this face. From the previous example, we calculated the natural frequency as 14 radians per second for spring value of 4,900 Newton per meter and a mass of 25 kilograms. So let us add in the value of the spring as 4,900 Newton per meter. It will automatically change to 4.9 Newton per millimeter as the unit set up in the assembly. For the free length, insert value of 400 millimeters, same as the distance constraint. For the display part, you can customize the spring appearance as you like. Click OK and head to the simulation window. Then disable the playback key. Select the plot icon. Select this mass face, and then select displacement, linear displacement, and X component. Go to Mates and suppress the distance constraint. Finally, click the calculation icon. From the plot we can see the line is flat and there is no vibration, hence the system is in equilibrium. To see the vibrations, go to Mates, unsuppress the distance constraint, and change its value to 420 millimeters. Click OK and head back and suppress the distance constraint again. click calculation icon, we can see the vibrations displayed on the plot. The magnitude equals 40 divided by 2, which is 20 millimeters, same as x. Then, we check the cycle time. We can see that the period to complete one cycle is 0.45 seconds. The natural frequency is equals to 2 times pi divided by this cycle time. We can see that its value is 13.962, which is close to 14 radians per second. So, our example validation is successful, and it can be modeled in real-life situation. That's all for this lesson. See you on the next lesson.